Carnot engine means? So the Carnot heat engine is the Carnot engine is a theoretical cycle proposed by Nicholas Leonard Sadi Carnot. Okay, it is an engine that operates between two temperatures. Those are T1 and T2, which gives the thermal efficiency of that engine and involves thermal and adiabatic process. Okay, here we study about the Carnot engine, its theorem. So different applications and related solve examples we have in our textbook. So before that, what is a Carnot engine? So a heat engine is devised to convert heat into the work. That is called the Carnot engine. So what is the Carnot engine? A heat engine is a device to convert heat into work. So that is called the Carnot engine. So what it is, the Carnot engine is a thermodynamic cycle that gives the maximum efficiency of a heat engine which works between two temperatures in reversible thermal and adiabatic expansion and compression process. We have here two types of expansions and two types of compressions we have here. One is adiabatic expansion and adiabatic compression. We discuss about this. So again, what is the work of Cot engine means? It works between two temperatures. Those we are discussed early. So that is the T1 and T2 with a hot and cold reservoirs. Means here what we are taking T1 and T2 both. One is hot and another was two reservoirs we are taking here. One is hot reservoirs, that is T1 we are taking, and cold reservoir, that is the T2 we are taking here. So these are two steps involved in this process. One is isothermal process at a temperature T1. What is the work? Absorbing heat Q1 from the hot reservoir. So here isothermal process at a temperature T1 is absorbing from heat Q1 from a hot reservoir. And next T2, what is the T2? Isothermal process at T2 when we will take, that is releasing heat Q2 from the cold reservoir. See, you see here on this monitor, the temperature T1 is absorbing heat Q1 from the hot reservoir. The temperature T2 releasing the hot Q2 from the cold reservoir. So here we are following four steps, simple steps here. So one is working substance, what we are using here, working substance, and source of heat and sink and insulating stand. Four parts we have here. One is a working substance, ideal gas we are taking here, and source of heat we are using hot to cold reservoirs, and one is a sink and insulating stand. What are the work is the sink and what is the work is in insulating stand, we will see here. You see this photo or this figure. So source at temperature T1 and insulating stand we are keeping here, sink at T2. Means here the source T1, this is a hot reservoir and this is a cool reservoir, cold reservoir. And what we are taking the substance is ideal gas. So this is called the piston, and this is whatever we are taking the cylinder. What is we are taking this cylinder? So this is a pistol. This we are using the blue one is a ideal gas. So this is a insulating stand. What is the work of this substance? How it will work? We will see here. So working substance when we are taking the ideal gas, enclosing in a cylinder piston. So arrangement, the cylinder is made with perfectly non-conducting walls and perfectly conducting base with a frictionless non-conducting piston. Okay, here frictionless we are taking here. Then what is here non-conducting means what here? Non-conducting means here whenever we are taking this uh, frictionless and non-conducting. So here we are taking these non-conducting walls ante. So walls that do not allow heat to పాస్ త్రూ దెమ్ అంటే దాంట్లో నుంచి హీట్ని ప్రాసెస్ కానివ్వ ఉండేటువంటి సిలిండర్ వీఆర్ యూజింగ్ హియర్. ఓకే, సో ద సబ్స్టెన్స్ వాట్ వీఆర్ టేకింగ్ హియర్ ఐడియల్ గ్యాస్ వీఆర్ టేకింగ్. అండ్ what is the source heat we are using here? It is hot reservoir or source which is having high thermal capacity maintained at higher temperature T1 degrees Kelvin, and the higher thermal capacity of the source is necessary so that on taking heat from no change temperature occurs. So what is the work of sink? This sink works a cold reservoir or sink maintained at a low temperature, that is T2 degrees Kelvin. It is having infinite thermal capacity. Any amount of heat can be given to it without changing any temperature. So here insulating stand. What is here insulating? Insulating means what? Insulating అంటే ఏంటమ్మా? Pushpanjali, who is Pushpanjali? Are you able to hear? Pushpanjali, you have to give response. అమ్మా
వినిపిస్తుంది మ్యామ్.
వినిపిస్తుందా? నువ్వు ఏ స్టడీ సెంటర్ తల్లి?
ఇబ్రాహీంపట్నం మ్యామ్.
Very good. You attended for practical classes?
ఎస్ మేడం.
Very good. Where? Dr. B.R. Ambedkar Open University only?
ఎస్ మేడం.
Okay, okay. Are you able to recognize me?
ఎస్ మ్యామ్.
Very good, very good. Thank you. Thank you for your response. Thank you. Yeah. Here, what is insulating? Insulating means what? Insulating means the process to creating a barrier to prevent transfers. This is called the insulating. We are using that insulating stand. The base of cylinder is kept on this non-conducting stand to make whole system to be adiabatic. So here early classes we are discuss about the some process, whatever the process in thermodynamic process. So 4 process we have here. So here what is the adiabatic process ante? Here a process where no heat transfer into or out of the system occurs. So this is called the adiabatic process. Yeah, come to the point of what is the operations involved in a Carnot cycle ante. A Carnot cycle is defined as an ideal reversible closed thermodynamic cycle. Okay, what is Carnot cycle? A Carnot cycle defined as an ideal reversible closed thermodynamic cycle. This is called the Carnot cycle. So here 4 operations involved in this Carnot cycle. One is here 2 expansions we have and 2 compressions. So isothermal expansion we have, isothermal compression also we have in this process, adiabatic expansion and adiabatic compression. During these 4 operations, the expansion and compression of the substance can be done up to the desired point of back to the initial state. So come here, these are the 4 steps we are using in Carnot cycles. So for these 4 steps, whatever we have, wait a minute. Thank you. Here we have four operators. One is operations here: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compressions. So in first step, we will get W1 is equal to Q1 is equal to nRT1 log E V2 by V1. What will happen here? This isothermal expansion of gas from P1 V1 T1 to from P1 V1 T1 to P2 V2 T1. So here what is here the T1? T1 transfers the heat. Okay. Here work done by the gas on the environment Q1 we are taking here, and absorbed by the gas from the reservoir a constant temperature. We are taking the constant temperature is a T1. So this heat transfers from 1 to 2. How? P1 V1 V means what am I ikkada? Volume, right?
Volume.
Yeah, pressure, volume and temperature. P1 V1 T1 to P2 V2, not T2, T1. Okay. What is this T1? T1 is a constant temperature, whatever we are using. So when we will get this, W1 is equal to Q1 is equal to NR T1 log E V2 by V1. From the first operation, we will get this equation. And come to the point of number 2, step 2. You see this from B to here. Start here from here to isothermal expansion, and from second one adiabatic expansion. So what is here adiabatic process? ఇక్కడ చూడండి, what is adiabatic process అంటే ఏంటి? A process where no heat transfers into or out of the system kada. So here adiabatic expansion of the gas from P2 V2 T1 only. ఇక్కడ నుంచే వస్తుంది కదా. P2 V2 T1 to P2 P3 V3 ఇక్కడ ఏమొస్తుంది? T2. యా, ఇక్కడ వచ్చేసి ఏమొస్తుందమ్మా? P1 V1 T1 to P2 V2 T2 T1 కదా. సేమ్ అక్కడి నుంచే మళ్ళీ థర్డ్ పొజిషన్కి వస్తుంది అన్నట్టు. సో థర్డ్ పొజిషన్కి రావాలంటే వాట్ ఈస్ ద ఈక్వేషన్? వీ హ్యావ్ P2 V2 T1 to P3 V3 T2. అంతేనా? సెకండ్ ఈక్వేషన్ వచ్చినప్పుడు T2 we will write here in the form of first thermal expansion T1 only. Here also T1 to again it will process P3 V3 to T2. Okay, this is the step 2. Then come to the point of step 3, isothermal compression. What will happen here? The gas from the ఎక్కడి నుంచి వస్తుంది? P3 V3 T2 to వెరీ గుడ్ చెప్పండి. P4 V4 T2 ఓన్లీ. అర్థమవుతుందా? మీ దగ్గర పెన్ ఉంటే నోట్బుక్లో రాసుకుంటే ఈజీగా అర్థమవుతుంది. ఓకే. సో P3 V3 T2 to P4 V4 T2 ఓన్లీ. ఓకే, ఇంకా ఇక్కడికి వెళ్ళలేదు. ఇక్కడికి వెళ్ళినప్పుడు అగైన్ ఇట్ విల్ కమ్. ఓకే. సో దిస్ ఈజ్ థర్మల్ కంప్రెషన్, isothermal compression. P3 V3 T2 to P4 V4 T2 only it will come. Then we will get the process. Here also the temperature is constant only. T2 also constant we have. And here in this work done in the second step in adiabatic expansion, work done by the gas in this adiabatic expansion, we will get the W2 is equal to NR by gamma minus 1. Very good. T2 minus T1 minus
T2.
Yeah. In third position in isothermal expansion, it will convert to P3 to P3 V3 to T2, then P4 V4 to T2, right? Then what equation we will get here? W3 is equal to Q2 NR log V3 by V2. See here.
Q2 is equal to kada madam.
Sorry. Yeah, this is equal to. Okay. Okay na? Yeah.
Okay.
సో దెన్ కమ్ టు ది ఫోర్త్. ఇంకా ఇక్కడ నుంచి ఇక్కడికి వచ్చేసింది, ఇక్కడ నుంచి ఇక్కడికి వచ్చేసింది. దెన్ ఫైనల్లీ వి విల్ గెట్ ది ఫైనల్ ఈక్వేషన్ ఈజ్ ఇన్ అడబాటిక్ కంప్రెషన్. ఇక్కడ ఏం తీసుకుంటాం మీరు చెప్పండి? P4V4T2
to P1
P1
V1
V1.
T1.
Very good. So the total Carnot cycle process is this one. We will get this equation. Okay. So W4 ఇక్కడ ఏమవుతుంది? In the fourth stage NR by gamma. ఇదే ఈక్వేషన్ చూడండి మీకు కదా, సేమ్.
Yes, ma'am.
These are the compressions kada, these are the expansions. When we will take the expansion, we will get these equations V2 by V1 and here V3 by V2. ఇక్కడ వచ్చేసరికి ఇక్కడ చూడండి T1 minus T2, T1 minus T2, same equation only. These are the Carnot cycle process. Okay, yeah. ఇక్కడ ఎక్స్పాన్షన్ అనేది మీకు ఎలా జరుగుతుంది అనేది I will tell you. The gas is taken from P1 V1 T1 to P2 V2 T1. Early time I told you know, where we'll take the heat is Q1 is absorbed from the reservoir at a temperature of T2. Q1 when will we get? That is the T2. Okay, temperature is T2. హీట్ అబ్జర్వ్ మనం ఏం తీసుకుంటున్నాము? Q1 తీసుకుంటున్నాము. టెంపరేచర్ రిజర్వాయర్స్ వచ్చేసి T1. సిన్స్ ద ఎక్స్పాన్షన్ ఈజ్ ద ఐసోథర్మల్, the total change in internal energy is 0. ఎందుకు 0 అవుతుంది అక్కడ? The temperature is there constant, no, then from starting.
Yes.
So that's why it is 0 and the heat absorbed by the gas is equal to the work done by the gas on the environment, which gives as this equation P1 V1 T1 is equal to P2 V2 T1. Okay. సో ఐసోథర్మల్ ఇందాక నేను చెప్పిండేదే ఇది. ఐసోథర్మల్ ఈక్వేషన్ ఏబి అనేది మనకు ఈ ప్రాసెస్లో జరుగుతుంది. లెట్ ద క్వాంటిటీ ఆఫ్ హీట్ అబ్జర్వ్డ్, ద ప్రాసెస్ ఈజ్ ద సేమ్ Q1 ఓన్లీ అండ్ హియర్ work is we are taking work done is a W1. What are the from our books I took here? This is I have to explain, no, that's why I took these equations and here from our books we have Q1 is equal to W1 is equal to integral V1 to V2 this process PdV is equal to integral V1 to V2 RT1 dV by V. So finally we will get this is the first equation. And also this is adiabatic expansion from B to C. And this is adiabatic expansion from B to C. What is the works done? We will get it. W2 is equal to integral V2 minus V3 PdV is equal to V2 minus V3 K Kelvin temperature we are taking. That's why we are taking K and dV by V minus gamma. So this equation it will come, right? So finally we'll get this R T2 minus R T1 by 1 minus R. Therefore P2 V2 is equal to R T1. P2 V2 is equal to T1 kada. P2 V3 is equal to T2. So this is the equation from the adiabatic expansion, in the adiabatic expansion. So this is isothermal expansion. So stage 3, this is stage 3 we will take. And this is adiabatic compression B2 finally A. So here efficiency of the engine we will calculate this. This is called eta is equal to work done by the engine by heat taken from source is equal to heat converted into work by the heat taken. So this is the equation efficiency of the engine. W by Q1 is equal to Q1 minus Q2 by Q1, that is equal to 1 minus
Q1
by Q1. We will get this. Okay, this is all from our book only. So the net work done by the gases will take W1, W2, W3, 4 process we have there, no, in the Carnot cycle. So that's why work done by the gas we will take W1, W2, W3, all plus we will take here. So we will get finally point B to C when it will transfers in adiabatic process or adiabatic process. T2 V2 power gamma minus 1 is equal to T2 V3 gamma minus 1. Finally, we will get that T1 by T2 that is equal to V3 by V2 whole power gamma minus 1. So again we will take A to D. అది మళ్ళీ రివర్స్ వచ్చినప్పుడు మనకి ఏమొస్తుందంటే T1 by T2 is equal to V4 by V1 from the equation of 7 and 8. అంటే ఇప్పుడు పైన ఉంది కదా, దిస్ ఇస్ ద 7 equation. So 7 and 8 we will get this equation. Finally V3 by V2 is equal to V4 by V1, or V3 by V4 is equal to V2 by V1. So this equation, ninth equation, we substitute in the sixth equation, we will get this W is equal to RT1 log of V2 by V1. So minus RT2 V2 by V1. Okay. సో ఈటా ఈజ్ ఈక్వల్ టు డబ్ల్యూ బై క్యూ. ఆ ఈక్వేషన్ మనకి ఎలాగొచ్చింది అనేది వీఆర్ షోయింగ్ హియర్. సో ఈటా ఈజ్ ఈక్వల్ టు 1 మైనస్ T2 మైనస్ T1. ఓకే, యా. సో కార్నోట్ సైకిల్ ఇంపాసిబిలిటీ ఏంటి అని అంటే మనకు, సో ఇక్కడ మనకు కొన్ని రీజన్స్ ఉన్నాయి. ఇన్ కార్నాట్ ఇంజన్ ద హీట్ ఈజ్ టు బి టేకెన్ అండ్ రిజెక్టెడ్ స్ట్రిక్ట్లీ అట్ కాన్స్టెంట్ టెంపరేచర్, which is particularly, which is partially very difficult to achieve the temperature. So the base of cylinder of the engine is assumed to be perfectly conducting, the other parts of perfectly non-conducting. This is not again feasible. Okay, so these are all the we have from our textbook only. So finally what we have here, it is perfectly reversible in its action. When the cycle is reversed, the working substance will be take an amount of Q2, we are taking of the heat from the sink, and gives out of the amount of the heat, the source, the engine. Actually ఏమవుతుందమ్మా ఇదంతా మీరు చదువుతున్నాం కదా, hence it is not possible to obtain the Carnot engine in practice. అంటే అర్థం ఏంటి? So this is the last class we have here. So what will happen here, we will go for little bit revision. So what we discussed in last classes, yeah. So we discussed zeroth law and first law of thermodynamics. See here the system, how the basic concept of thermodynamic system. So this system work, heat, system, surroundings. This is the isolated boundary. So what is the systems? We have total 3 systems: isolated system, closed system, open system we have. So what is the isolated system, what is the closed system, what is open system ante? So an isolated system cannot exchange energy and mass without its surroundings. Closed system ante oka room is the one example. An isolated system cannot exchange energy and mass without its surroundings. Okay, and open system ante anything will happen. Okay, so and again surroundings ante enti, thermodynamics process etla untundi. What is the thermodynamic process ante? A system undergoes a thermodynamic process when there is some energetic change within the system that is associated with the changes pressure, volume and internal energy. Okay, so 4 process I told you, 4 process we have here: adiabatic process, isochloric process, isobaric process, isothermal process. These 4 process in thermodynamic process, these are the main important the process, even though starting to ending. So we will use these 4 process. Okay, and here what is the equilibrium, thermodynamic equilibrium anante? We have here, yeah. When the temperature is the same throughout the entire system, we consider the system to be in thermal. ఎప్పుడు అనుకుంటామమ్మా థర్మోడైనమిక్స్ థర్మల్ ఈక్విలిబ్రియంలో సిస్టమ్ ఉంది అని చెప్పి? Mainly we have 3 types of equilibriums. One is thermal equilibrium, mechanical equilibrium, chemical equilibrium. What is the thermal equilibrium ante? When the temperature is the same throughout the entire system, we consider that is in thermal equilibrium. So what is the mechanical equilibrium ante? When there is no change in pressure at any point of the system, we consider that is in mechanical equilibrium. So what is the chemical equilibrium ante? When the chemical composition of a system does not vary with time, we consider that is the chemical equilibrium అని చెప్తాం. సో యాక్చువల్లీ ఏంటి థర్మో డైనమిక్ ఈక్విలిబ్రియం అంటే ఏం చెప్తుందంటే ఇఫ్ ఇట్ ఈజ్ ఇన్ కెమికల్ ఈక్విలిబ్రియం, మెకానికల్ ఈక్విలిబ్రియం, సో థర్మోడైనమిక్ ఈక్విలిబ్రియంస్ ఈ 4 అని చెప్తుంది, 3 అని చెప్తుంది. సో మనకు మెయిన్లీ ఎన్ని లాస్ ఉన్నాయి? జీరోత్ లా, ఫస్ట్ లా, సెకండ్ లా, థర్డ్ లా లిటిల్ బిట్ వి డిస్కస్ ఇన్ అవర్ సిలబస్. సో వాట్ ఈస్ ద జీరోత్ లా అని అంటే, జీరోత్ లాని డెవలప్ చేసిన వారు ఫ్లోయర్ డెవలప్డ్ ఇన్ 1930s. జీరోత్ లాని ఈయన డెవలప్ చేయటం జరిగింది. జీరోత్ లా స్టేట్స్ ఏంటి అంటే ఏం చెప్తుంది అంటే, టూ సిస్టమ్స్ ఆర్ ఈచ్ ఇన్ థర్మల్ ఈక్విలిబ్రియం విత్ ద థర్డ్ సిస్టమ్, then those two systems are also in thermal equilibrium with each other అనేది మనకు జీరోత్ లా చెప్తుంది అన్నట్టు. ఓకే,
Madam,
Why is not clear, ma'am? Mama,
ఓకే. సో మనకు ఇక్కడ యా, సో జీరోత్ లా ఆఫ్ థర్మోడైనమిక్స్ అనేది మనకు ఏబిసి, మనం ఏమని చెప్తున్నాము, థర్డ్ సిస్టమ్, దోస్ టూ సిస్టమ్స్ ఆర్ ఆల్సో ఇన్ థర్మల్ ఈక్విలిబ్రియం ఆఫ్ ఈచ్ అదర్ అంటున్నాం. ఇక్కడ చూడండి ఏబిసి ఉన్నాయి, ఈ రెండు వచ్చేసి థర్మల్ ఈక్విలిబ్రియంలో ఉన్నాయి విత్ థర్డ్ సిస్టమ్ సితో. సో ఇది కూడా వన్ ఆఫ్ ది ఎగ్జాంపుల్ టు అండర్స్టాండ్ ది జీరోత్ లా ఆఫ్ థర్మోడైనమిక్స్. ఓకే, సో టెంపరేచర్ ఆఫ్ సిస్టమ్ ఏ ఈజ్ ఈక్వల్ టు టెంపరేచర్ ఆఫ్ సిస్టమ్ సి. Similarly, if B is in thermo equilibrium with system C, ఇప్పుడు చూడండి దీన్ని అండర్స్టాండ్ చేసుకోండి కదా. దెన్ టెంపరేచర్ ఆఫ్ బి వచ్చేసి ఈజ్ ఈక్వల్ టు టెంపరేచర్ ఆఫ్ బిసి కదా. అంటే ఈ మూడు అనేవి మనకు ఏం చెప్తున్నాయి, each of thermal equilibrium third system, then those two systems are also in thermal equilibrium of each other అని సేమ్ సిస్టమ్. అండ్ ఇది కూడా వన్ ఎగ్జాంపుల్ మనం తీసుకోవచ్చు. ఒకసారి మనము కన్సిడర్ 2 cups అనేది, దిస్ ఈజ్ ఆల్సో వన్ ఎగ్జాంపుల్ ఐ గివెన్ హియర్. అండ్ వాట్ ఈస్ ద సిగ్నిఫికెన్స్ ఆఫ్ ద జీరోత్ లా ఆఫ్ థర్మోడైనమిక్స్ అంటే, ది జీరోత్ లా ఆఫ్ థర్మోడైనమిక్స్ ఈజ్ అ బేస్ ఫర్ థర్మల్ ఈక్విలిబ్రియం. ఓకే, and it provides temperature as the indicator for thermal equilibrium. So thermometer function on the basis of this law. Thermometer works on this basis of zeroth law. Okay, so and first law of thermodynamics, what is the first law of thermodynamics, and ఇవన్నీ కూడా మనకు దిస్ ఈస్ ద ఈక్వేషన్ ఆఫ్ ఫస్ట్ లా ఆఫ్ థర్మోడైనమిక్స్. ప్రీవియస్ క్లాసెస్ we explained about this. This is the one example for this first law of thermodynamics. Okay, so what is the first law of thermodynamics అని అంటే, a thermodynamic system in equilibrium state process at a state variable known as the internal energy E between these two systems, change the internal energy is equal to difference of the transfers into the system work done by the system. This is one example for first law of thermodynamics. What is the significance of first law of thermodynamics అంటే, zeroth law of thermodynamics works on the thermometer. ఓకే, మనం ఇప్పుడు థర్మోమీటర్ చూస్తుంటాం కదా, సో దట్ వర్క్స్ ఇన్ zeroth law thermodynamics. ఓకే, సో ద సిగ్నిఫికెన్స్ ఆఫ్ ఫస్ట్ లా ఆఫ్ థర్మోడైనమిక్స్ ఏంటి అంటే, ఇట్ రిప్రజెంట్ ద ఎనర్జీ దట్ క్యాన్ బి ట్రాన్స్ఫర్ ఫ్రమ్ వన్ బాడీ టు అనదర్ బాడీ, బట్ ఇట్ కెన్ నాట్ బి క్రియేట్ నార్ డిస్ట్రాయిడ్. సో ఇక్కడ మనము dq and dw changes throughout the process. However, we will get the du is equal to dq minus dw, where du is equal to internal energy and heat added q we are taking, w is the work. So limitations of thermodynamics also we used, and applications of thermodynamics, first law of thermodynamics ante refrigerators, thermal power plants, engines. So these are all the applications of the, and also these are also applications for this first law of thermodynamics: isothermal process, adiabatic process, isochronic process, and isobaric process, a cyclic process. These are all the first law of thermodynamics. So applications of first law of thermodynamics: reversible and irreversible process example ga తీసుకోవచ్చు. So isothermal process lo we will get dq is equal to du plus dw. This is the process, and adiabatic process will go for du is equal to minus dw. Mainly this is the first law: dq is equal to du minus plus dw. So isochoric process lo వచ్చేసి we will get this equation: dq is equal to du, dq అంటే heat, and du అని అంటే internal energy. The applications of thermodynamics law we will get at the time of cyclic process, when we will use in first law of thermodynamics, we will get this equation becomes as dq is equal to dw. Isobaric process లో కూడా మనము dq is equal to cp dt plus pdv అనే ఈక్వేషన్ మనకు వస్తుంది when we will apply the first law of thermodynamics. Okay, these are the reversible and irreversible process. Reversible process and irreversible process lo many such systems can be systems and surroundings be brought back to their initial state. Avuna kada? So for example, with a common example such as rusting and formation, we can say that it is not possible most cases. Okay, reversible process ante enti, conditions of reversibles, and a example of reversible we will use, and a reverse irreversible process, and these are all we discuss in last classes, last 5 classes. This is the last sixth class. So here a comparison between reversible and irreversible also we discuss previous class. So the process occurs slowly, and this is very rapidly, and equilibrium is not disturbed in reversible. The equilibrium may alert or may attain only after the process completion, when it will involve. Work done is a maximum. Here work done is in not maximum, little bit of minimum. So can be easily reversed in this reversible process, cannot be reversed. Okay. So these are the forward and proceed in the forward and backward direction. This reversible process we can do. Can occur in one direction only, this irreversible process. Okay. Second law of thermodynamics ante enti అని అంటే, so the second law of thermodynamics is the fundamental principle in thermodynamics that describe the direction of natural process and the concept of entropy. It has several formulations, but they are all revolved around this the certain spontaneous process or reversible lead and lead to an increase. This is so this concept is often summarized mainly increases of entropy. So this is several statements we have in the second law of thermodynamics. These are the statements. Clausius statement. What Clausius told that heat cannot spontaneously flow from a colder body to a hotter body. So Kelvin Planck statement also we have. It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. He is telling the statement. What is the entropy statement ante? The entropy of an isolated system never decreases. It either remains constant in reversible process or increasing in the irreversible process. So these are mathematically we proved. This is all, and these are the applications. Application of second law of thermodynamics. Now only we discuss about heat engine. That is one of the example for application of second law of thermodynamics. when we will take the real example of for second law of thermodynamics. So we discussed earlier classes thermodynamic. What are the thermodynamic potentials? And those thermodynamic potentials are we discussed in internal energy U, enthalpy H, and Helmholtz free energy F, Gibbs free energy G. These are all the equations for those whatever we discussed in thermodynamic potentials. Internal energy when we will take, so we will get this du is equal to TdS minus PdV. Enthalpy will get H is equal to dH is equal to TdS plus VdP. So here you all of you see in this internal energy, U is into SV. Here the constant is U. So internal energy, and here H enthalpy SP we will take, and these are the Helmholtz energy equation, Gibbs functions, and properties of all these Helmholtz energy and Gibbs functions, internal energy, all this enthalpy, Helmholtz energy and Gibbs energy, we will get this. Finally, we will get this thermodynamic potential are these four. Du is equal to TdS minus PdV, where we will take U into SV, dH TdS plus VdP, H is equal to SP, dF is equal to minus PdV minus PdT, and dG is equal, this is the Gibbs law. And what about this? dF, Helmholtz function. F unte Helmholtz, H unte enthalpy. Okay. And G unte Gibbs, U unte internal energy. Okay. So Maxwell relations also we discussed in last class, the thermodynamic equations and applications also. These are the Maxwell's equations we saw in last class. These are all the, we discuss Maxwell relations with this internal energy with internal energy, and enthalpy Maxwell relation we will get this one, and Helmholtz free energy Maxwell relation how it was, and also Gibbs free energy Maxwell relations. And these are all the Maxwell relations with the four thermodynamic potential. These are the final, we will get that thermodynamic potential equations with the relation of Maxwell's equation. So applications of Maxwell's thermodynamic equations. We have Clausius equation and latent heat also we discussed. So Joule Kelvin also we discussed in last class, and low temperature also we discussed. So what is the low temperature ante? So physics tells that study of how matter and system behave the very low temperatures. Okay, this is the temperature, low temperature. Physics, we have superconductivity, superfluidity, and quantum Hall effect, Bose-Einstein, and these are all we use in low applications of low temperatures. So, for example, we have this is also we discuss క్రయోజెనిక్ డిసీజ్ అంటే ఏంటి అనేది కూడా అది ఎందుకు వస్తుంది అనేది కూడా we discuss in last class. Okay, so applications of low temperatures in physics also we discuss the refrigeration we discussed last class, and these are all commercial refrigeration cycle also we have. Vapor compression of refrigeration we discussed, and black body radiation yesterday we discussed, and black body radiations of we have two concepts, classical and quantum, and black body radiation of uh, so we will explain about this Wayne's displacement from our textbook only, and reliant genes also we discuss. Today we discussed these are all yesterday's class. Today we discuss Carnot heat engine, the Carnot heat engine, how it will work, the Carnot engine. What is the Carnot engine? We discuss it today's class, and what it works T1 and T2, hot to colder reservoir we will take there, and mainly four consist heat engine following four parts: working substance, source of heat, sink, insulating state. So this is hot, and this is the coldest. From here to here it will transfer, and this is the substance we will take. This is insulating stand, and working substance. What is the work of working substance, and what is the source of heat, and sink, insulating stand. What is the insulating stand? What is the insulating? Also, we discuss in this insulating stand. We expressed about adiabatic process and what is the main Carnot cycle depend on the ideal reservoir closed thermodynamic cycle. These are the four successive operators we discuss with this figure. We'll get this is and from our textbooks whatever we have the equations we discussed today's class. Okay, so this is finally we are completing all these online classes. Okay, today this is the last class. Okay, so you have exams in the next month, no? Next
Yes,
month you
ma'am.
have exams, na? Okay,
Mm.
you just go through this whatever I discussed, those are the important. You see your textbooks and mm, read. Okay, all the best for your exam. Okay, na? Thank you, ma. Thank you. Right.
Ma'am,
Yeah.
20 marks కి ఏ టాపిక్ ప్రిపేర్
That
అవ్వాలి
is
మ్యామ్?
అండర్స్టాండింగ్ క్వశ్చన్స్ వీఆర్ గివింగ్ మా. ఒక క్వశ్చన్ అటాచ్ చేసి దాని మీద అండర్స్టాండింగ్ అప్లికేషన్స్ మీద ఇప్పుడు వి డిస్కస్ ప్రీవియస్ క్లాసెస్ అప్లికేషన్స్ ఆఫ్ థర్మోడైనమిక్స్ అట్లా ఉన్నాయి కదా, వాటి మీద హాఫ్ క్వశ్చన్ ఉంటుంది 20 మార్క్స్లో. హాఫ్ క్వశ్చన్ రిలేటెడ్ ఫ్రమ్ యువర్ టెక్స్ట్ బుక్. ఇప్పుడు
ఓకే.
ఫర్ ఎగ్జాంపుల్గా ఫస్ట్ ఎక్స్ప్లెయిన్ ద ఫస్ట్ లా ఆఫ్ థర్మోడైనమిక్స్. సో వాట్ ఆర్ ద అప్లికేషన్స్ ఆఫ్ థర్మోడైనమిక్స్, వాట్ ద ప్రాసెస్ ఇట్ విల్ టేక్, అది అండర్స్టాండింగ్కి వస్తుంది కదా. సో అందుకని అండర్స్టాండింగ్ మీద ఉంటుంది, డైరెక్ట్ క్వశ్చన్ హాఫ్ ఉంటుంది, హాఫ్ క్వశ్చన్ మీద అప్లికేషన్ ఉంటుంది, అండర్స్టాండింగ్ ఉంటుంది.
ఓకే మ్యామ్.
ఓకేనా? ఓకే అమ్మా. సో ఆల్ ద బెస్ట్ ఫర్ యువర్ ఎగ్జామ్స్. రైటా? థ్యాంక్
థ్యాంక్
యూ.
యూ మ్యామ్.
థ్యాంక్ యూ. రైట్.
Thank you, ma'am.
ఓకే అమ్మా. ఆల్ ద బెస్ట్.